Good afternoon, and thank you for joining us on our call today. My name is Jason Tilgis from Transcat, and I'll be your moderator this afternoon. Our webinar topic is how to calibrate an RTD using a dry block calibrator. This topic is being presented by Ron Ainsworth from Fluke Calibration. Ron is the business manager for process calibration tools at Fluke Calibration. After graduating with a degree in physics in 1998, he started in the primary temperature calibration lab in American Fork, Utah. He has since had roles as a laboratory manager and as a marketing manager at Fluke. We expect today's presentation to last roughly 30 minutes, and then we'll answer any questions that you may have submitted. At any time during the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation within about a week of this presentation. At this time, I'm going to turn the presentation over to Ron.
Well, hi everybody. I'd like to thank you for coming to today's webinar sponsored by Transcat. We're going to talk about how to calibrate an RTD using a dry block calibrator. The agenda is going to be something like this. We're going to have a dry block introduction. We're going to talk about some of the sources of error that can affect a calibration, the uncertainties thereof, and we're going to talk about how to solve some of those problems related to those errors if we need a more accurate calibration. We'll talk about how to calculate the uncertainties and then get into some issues like, well, what do I do if I've got an odd-shaped probe that doesn't really fit into a dry block very well? Or what if my temperature range I need to cover is wider than the dry block that I have? Liquid and glass thermometers pose a particular challenge. And so then we'll talk about an example of an RTD calibration, and then talk through how to take care of your dry block, keep it maintained, so that it's going to continue to provide useful calibrations for you. So real quick, we'll do kind of an overview of temperature sensor calibration. Temperature plays an important role in many industrial processes. It's for example, pharmaceutical sterilization, for example, metal heat treatment, cold storage, atmospheric and oceanographic research. There's all kinds of different places where it becomes important, but why do the temperature sensors themselves need to be calibrated? A lot of folks not even sure that it's necessary or possible. But all temperature sensors are going to drift over time, and especially since they're going to be exposed to high and low temperatures and cycled and that sort of thing, the sensor is going to drift. And in fact, the temperature sensor, like if you look at a system like this, the largest portion of the error is going to be coming from the temperature sensor. And so it's kind of a shame that in many cases we don't even have processes to calibrate anything but the electronics that are connected to the temperature sensor. So we're going to talk about how to fix that today with using a dry block calibrator. Let's see. Oh, and so just kind of to point out here one other thing related in terms of what you use to calibrate the electronics of a system like this is like a Fluke 754 or a Fluke 726. You can check the 4 to 20 milliamps. You can pass a simulated temperature signal and compare the output on a temperature indicator. But that is just part of the process of doing the calibration. To include the temperature sensor, we're going to need a dry block calibrator, and so that's what we're going to talk about now. So let's say we're going to do a temperature sensor verification using a dry block. First thing that you're going to do is put the temperature sensor, as illustrated here, into the dry block. In particular, there's usually going to be an insert there, and the inserts are often removable so that you can handle different sizes of probes. When inserted, that probe ought to be fully immersed, which means you'd like the tip of the probe to be bottomed out at the bottom of that of the insert, and that would put it level with the temperature sensor in the dry block, which you're using for the comparison. So when you look at the display on the dry block, it's reading a temperature that comes from a temperature sensor that's going to be down at the bottom of the dry block. There's some issues that we're going to talk about later that have an influence there. It becomes kind of important that, for example, the temperature at the bottom of that block is not the same as the temperature at the top of the block. So here is an example, though, of what a calibration might look like. I'm gonna start, for example, at the lowest temperature. And the reason I might want to start at the lowest temperature rather than the highest temperature is, one, dry blocks actually are faster going up from ambient rather than down. The other thing is that a dry block calibrator, when you take a probe to a high temperature, if it's a high enough temperature, you're actually going to, if there's strain in the probe, you're actually going to influence the behavior of the probe. It's going to start to what we call anneal, which is going to remove some of the stress from the probe. And so you're trying to collect as-found data. You kind of like to know what was this probe like at the beginning, before I even started to calibrate. And to do that, you really want to start at the lower temperature. So let's say I start at 0. I'm going to measure, I'm going to let it stabilize for maybe 15 minutes, and then I'm going to take a reading of the resistance of that probe, or I could take a reading of the indicated temperature if it's connected to a PLC or a display of some kind. When I'm looking at that temperature, if I could, well, let's start back. If I am looking at the resistance, I'm going to need to look at either a resistance table for a standard RTD, or I'm going to need to convert that resistance to a standard temperature for that particular probe. Each RTD will have a specific curve that defines what the temperature is at a specific resistance. So I might look at a table, might have to do some interpolation, but what you will do is compare the indicated temperature to what the true temperature is supposed to be, and the dry block will provide that true temperature in this scenario. We'll talk about other scenarios as well where I might have a different reference temperature standard. So once I've compared the two temperatures together, I need to determine whether it's in tolerance or out of tolerance. So it might be a Class A RTD, and then in this case at 0, plus or minus 0.15 degrees Celsius would be the tolerance. I would want to see if it was in or out. In this particular example, I showed the indicated error is a full degree Celsius, so that would be out of tolerance. When you look at this table and you go down to 100 degrees Celsius, that's the far left column, tells you what temperature we're at. At 100 degrees Celsius, if you move over to the fourth column, the indicated error is 0. So, wow, it's right on. And so it's intolerance at that point. Unfortunately, at every other point in this calibration, it was out of tolerance and for a Class A RTD. But if you looked at a Class B RTD, the 200 and 300 degrees Celsius, well, no, 200 degrees Celsius I'm still in, but at 300 degrees Celsius I'm out again because it's I was out by, my error was minus 2 degrees Celsius and my tolerance was 1.8. So this is kind of an example of how you go about thinking through, okay, did the calibration pass or fail? Now that's for a verification. That's the kind of sensor that maybe you don't provide any special calibration coefficients for. You just want to see if the Class A probe or Class B probe is in or out of tolerance, and you toss it if it's out and replace it. Now there's another scenario that you could do where where it involves actually producing calibration coefficients, and we will talk about that later in the seminar. So a quick introduction to what a dry block is. Dry block doesn't have a fluid; it's dry. So that's a useful feature in a lot of places where you really don't want to have a fluid because you're concerned about cleanliness or something of that nature. It's also convenient because you can change the temperatures quicker than you can a fluid. A dry block may not be quite as accurate as a bath, a fluid bath, but they can reach laboratory levels of accuracy. We call them moderately accurate. They have a fixed hole diameter, so the insert has holes drilled in it that are a fixed size. There's not much you can do to change the size once it's there, although you could replace an insert with another insert. The probe needs to fit snugly inside of the holes, and so you're careful to choose an insert that matches the type of probe that you need to calibrate. they have a fixed immersion depth. So you really ought to be pushing the probe all the way down to the bottom. If you have a really short sensor, that produces some issues that we will talk about how to solve a little bit later. The dry block is portable, which is a fantastic quality of it. These handheld ones you might take all the way up a catwalk and go and calibrate at a location that you need to. And we already talked about how these things are fast and what the internal probe looks like. So we'll go ahead and scoot to the next slide. So dry blocks are great. They're a very important tool in our calibration toolbox. But it's important to understand that there are certain sources of error that can influence the accuracy of our calibration. So we're going to talk about immersion effects, stem conduction, well contact errors, display accuracy, stability, both radial and axial uniformity, and one called loading, which has to do with how many probes you actually have inside of the dry block. So first off, with our display accuracy. Display accuracy on a Fluke dry block calibrator is the sum total of all of the errors inherent in the dry block calibrator. So all these others that we're going to talk about are just components of the total. The total is referred to as the display accuracy. So that's the accuracy I get when I'm looking at the display of the dry block. So that should be pretty easy to understand. It's generally a one-year specification on the spec sheet. Certainly for all the Fluke instruments it is. It includes the internal control sensors that are inside of the dry block that we talked about earlier. It's going to be down at the bottom. Because it needs to be pretty robust so that you can carry it around and it's not going to get knocked out of calibration just because you carried it from one location to another. We have to make it more resistant to that kind of damage. When you do that, unfortunately, it limits the accuracy that you can get from such a probe. And so the display accuracy of a dry block is actually higher than it optimally would be. And so, or higher. The uncertainties are higher. The accuracy is lower or worse than it otherwise would be. And so we have some things we can do to actually improve the accuracy when we use something called a reference probe, which we'll talk about later. But this display accuracy, it will be one of the largest contributors to your total overall uncertainty, especially if you're using it straight off of the data sheet rather than use some of the techniques we'll show you in a moment. So another issue is stem conduction. Stem conduction is the degree to which the heat leaks out of a probe when it's inserted inside of the dry block calibrator. So if you're at a high temperature, you're outside in ambient, it's going to be like 25 degrees C, and hopefully the probe is not going to be so hot that you can't touch it, but it should be it'll probably be a little bit warmer than ambient. But because you've got this differential between the temperature inside the dry block and the temperature outside, and the temperature of the probe outside, heat's going to flow from the hot end to the cold end, and that's actually going to reduce the temperature of the sensor, and so you're going to get an error related to stem conduction, and that's going to be impacted by how well you are fitting to how close the diameter of the probe is to the diameter of the insert. So there shouldn't be too much of an air gap. In fact, we'll talk about how big that air gap will be. Other things that influence this stem conduction is the materials that the probe is made out of, and how thick the walls of the metal are of the probe sheath. The different things like that can affect it. But generally, using a rule of thumb of 15 times the probe diameter plus the length of the sensor, which is usually about an inch, you can figure out about how deep you need to have the probe inserted so that you don't have big error due to stem conduction. So that it'll be something that you can almost ignore. Related to immersion effects is also something called a gradient. So as I mentioned before, dry block is going to have a different temperature at the bottom than it will up at the top. Now some dry blocks are going to have zones so that you can actually separately control the top temperature and the bottom temperature and try to reduce that differential between the top and the bottom, but there still is going to be a temperature difference between them. And if you measured the temperature from top to bottom and graphed it, you're going to see that the temperature varies as you move through. So it's kind of important to get the probe fully immersed when doing the calibration. So other solutions to this issue of, well, I've got a shorter probe and I can't reach all the way to the bottom of the dry block. What do I do? Well, we know that we need to have the sensor that is the reference and the sensor that is under test at the same level. So one trick would be you insert your probe and then you insert the reference, and you make sure that you have a reference thermometer inserted to exactly the same level as your unit under test. That's true even if you push it all the way to the bottom, or if you had to raise it up a bit to match the location of your probe. That would be a way of improving the accuracy, even though you're not able to be fully immersed all the way to the bottom. And but the other thing that this does is when I use an external reference thermometer, my uncertainties improve significantly. And I'll show you more about that when we get towards the end of the presentation and we start talking about calculating uncertainties. Oh, and just maybe one other thing I'd like to point out is that with many of the Fluke dry block calibrators, there's actually input for your reference thermometer. So you don't have to carry around a separate indicator for your reference thermometer. You could just plug a probe right into the front of the 9142 or 9143, for example, and it will immediately display the reference temperature on the display. But you'll get all of the advantages of the improved accuracy. So anyway, that's an important thing to be aware of. Next, well, I mentioned this before, that you want a snug fit between the probe and the insert. So if you have one common mistake that is made is people will get an insert with a really large hole, like say a half-inch hole, and they think, well, I can just stick anything I want in there. The problem is when there is a large gap between the insert walls and the diameter of the probe, you're going to have large errors in the temperature, because that stem conduction effect is going to start from the very bottom of the probe, and instead of at the interface of the top of the block to the probe. So that could be really disastrous. So what you're looking for is something between 0.005 and 0.01 inches of a gap between the probe and the insert. That's pretty snug. And it's probably something you're probably not going to get calipers out to measure it, but it's just the idea is it's going to be pretty snug, but it's still going to be loose enough that you can pull it in and out. You don't want it to get jammed in there. I've seen guys that have they got their probe stuck inside of the insert, and they grab the probe with two hands and they put one foot on the dry block and they yank real hard, and that damages the probe. It'll get bent. When I worked in the lab, you could always tell who'd done that. There's some telltale scratches, some bends. You'll never be able to fit it in a dry block again, that kind of a thing. But if you got a probe that you can't fit into a dry block, we'll talk about what to do about that later. So dry block stability. You need a stable temperature source in order to perform a calibration. So there's two kinds of stability. There's stability that in the short run, like say over a 30-minute period, like such as the graph here might suggest. It's a little more than 30 minutes, like 100 minutes is what's being shown. But you've got the short term, and then there's long-term stability. We often call it drift, where maybe I'm looking at the difference of the reading over a period of 90 days or 6 months or a year. And so, but in the short term, I'm going to be concerned about that stability, because my ability to provide a good calibration and be certain of the temperature value is going to depend greatly on that stability. Especially if I'm using an external reference thermometer, the stability becomes a pretty significant component in my uncertainties. Now with a dry block, you can actually get in there and control some of the settings like the proportional band and things like that if you think it's not stable enough. Usually things are set correctly though, so that sort of thing would not be necessary. Another type of uncertainty that I mentioned earlier was uniformity. So axial uniformity is talking about the difference between the top and the bottom of the block. It's the change in temperature, along the insertion along the insertion point along the well. That's the axial uniformity. So if I have, this illustrates a problem. The illustration here. I've got a unit under test at the top with a very short probe. I've got my reference thermometer, the reference all the way down at the bottom. When I compare those two together, there's going to be a large uncertainty in the accuracy of my calibration because there's a big difference between the temperature at the bottom and the temperature at the top. So in modern dry block calibrators, the axial uniformity ought to be specified. So the metrology wells, the field metrology wells, you'll see that those are all specified uncertainties so that you can determine if I'm using a shorter probe, well, how bad is the error? If, on the other hand, I am comparing a reference thermometer to a unit under test and there are two different holes, I'm going to be pretty concerned about the radial uniformity. Also, if I just kind of want to understand, well, how big is the difference between all the temperature for all these probes that I got packed inside of my dry block, the radial uniformity gives you an understanding of that. So in this case, like for a field metrology well, we'd be talking about 1/100th of a degree is the impact due to radial uniformity. So the next uncertainty that we'd be concerned about is called loading. So the larger the instrument that I put inside of a dry block calibrator, like for example, if I've got a thermal well in there, that's going to have an impact on loading. Or let's say I put 3 or 4 probes inside of the dry block. That's going to also impact the uncertainty caused by loading. You've got heat being pulled out of the dry block by all these different probes, and there's more thermal mass. It has an impact on the uncertainty. So just to be aware, and also, as you can see, it's like for the loading effect for the field metrology well is 6/1000ths of a degree. So that may not even be enough to matter, but we have it characterized. So now, when I have all of these uncertainties, I'm going to want to calculate what the total uncertainty is. If I'm, like, say, for example, I'm going to use that external reference thermometer and I want to make a determination of, okay, what are my improved uncertainties? How much better is it? I can take all these different components off of the spec sheet and I can combine them together in a special way that we call RSS. RSS stands for root sum squares. So you can see I've got squares of a bunch of numbers. So like B1 is squared and B2 is squared and B3 is squared. Those are the squares. They're summed together, that's indicated by the plus signs, and the root is over the top of it. So you take the square root of that total to get to the root sum square. This is how you combine all of the uncertainties together. That produces a smaller number than you would get if you were to just add B1, B2, and B3 together. And it's the correct way to do it. So, for example, if my reference thermometer is 0.05 degrees Celsius, and my stability is 0.1 degrees Celsius, and my uniformity is plus or minus 0.02 degrees Celsius, I can square each of those numbers, add them together, and take the square root, and the result would be 0.113. But if I were to just add them together outright, it'd be 0.17, and so there's a difference, a significant difference between those two results, 0.17 degrees Celsius and essentially 0.11. So what do these uncertainties look like in your uncertainty budget? Or this is kind of what it would look like also to a degree on a spec sheet. You'd find all these numbers loaded on the spec sheet. So you go and take your axial uniformity, your radial uniformity, your loading effect and stability, all these things. You're going to try to add them all together. So one approach is you could just take all those and root sum square them the way I showed you in the previous diagram. and that's going to get you a number that's going to be pretty darn close. Now, if you are more of a if metrology is something that is more of a concern in your environment, you can do something that's just a little more precise. And so what, based on the specifications, are supposed to be your tolerances for the instrument. You know, the tolerance for the axial is 20 millikelvin, or that's the equivalent of 0.02 degrees Celsius. That you take that number and you divide it by the square root of 3, and that will convert it from a rectangular distribution to a standard uncertainty. So that gets you from 20 to 11.55. And that's what's been done to all these numbers, so that you go from the numbers on the left that were on the spec sheet to the numbers on the right. They create something called a standard uncertainty. You may not care about it. That's fine. I just need to let you know. Then you combine these together with an RSS, you get 14.32. So that, use that little equation we looked at just a moment ago. I'll jump back. You use that little equation, and that gets you to 14.32 millikelvin. I'm sorry for using millikelvin on this. That's how we had it written on in our data sheet. That is equivalent to 0.014 degrees Celsius. So there is an application note referenced here at the bottom that these tables are from. And I'll point that out to you. That we're also going to send the little application note to you after this webinar. But it's called Understanding the Uncertainties Associated with the Use of Metrology Wells. So you can, if you feel like digging into this a little bit more and understanding it a bit better, that'll be available to you. Now this, by the way, I'm sorry for jumping along, this is what the uncertainties look like if I use an external reference thermometer. My total expended uncertainty, K equals 2, that means it's got a 95% confidence interval, would be 0.28 degrees Celsius, or 29 millikelvin, 0.29 degrees Celsius, which is a pretty good number. That's not bad for a dry block, and that's what I get if I can use an external reference thermometer. If I, on the other hand, just use the display uncertainty, so I haven't reduced that. It's called control sensor accuracy. It's like the second one from the bottom. If I keep that in there instead of using the reference thermometer, then my total combined uncertainty winds up being 168 millikelvin, or that's 0.168 degrees Celsius. So a very large difference in the accuracy that you get, depending on whether you use an external reference thermometer or you just use the dry block alone. So I just let that sink in for a second. It's pretty important if you're trying to get more accuracy. Okay, so we said that we talked about what to do for odd-shaped probes. Let's say I bent a probe, or maybe I've just got a probe that is supposed to be an unusual shape. Maybe it's supposed to be bent, or maybe it's got some funny connections at the bottom, or there's different things that can, attachments that maybe you can't get off, that I can't fit it inside of a dry block. Well, one of the options is you use a micro bath instead. So you don't it's not dry anymore, and it's going to take a little bit longer, but the accuracy will be improved, and you can handle short sensors much more effectively. You won't have so much stem conduction when it's a fluid instead of a dry block. Also, you can fit them in there, and you can also fit a liquid and glass thermometer and do a calibration in a microbath in a way that you really can't do with a dry block calibrator. So microbath is an option to consider if dry block just isn't appropriate for your application. Another thing that we said we talk about is, okay, well, what if my probe has a wider temperature range than my my dry block? Can I use more than one dry block? And yes, of course. It doesn't matter if you have multiple calibrators. You can, for example, if I had a probe that needed to go from -95 to 200 degrees Celsius, you can see in the upper right here I've got this model 9190A that goes from -95 degrees Celsius all the way up to 140. It doesn't get me to 200. So I could also have, for example, a model 9143. And take the last point at 200 in that dry block. It makes it harder to automate the calibration and do the whole thing. You'd have to manually move it from one to the other, but there's no reason you can't do the full calibration and use multiple dry blocks to do it. So mentioned these the liquid and glass thermometers earlier. So if you have to calibrate liquid and glass thermometers, you have that option of using a microbath. I just wanted to point out that mercury and glass thermometers are kind of on their way out. There's many environmental concerns about mercury. You probably don't need anyone to tell you that. What I did want to tell you is that we do have a replacement for it, a digital probe called the 1551A, and there's also a 1552 that is pretty much a easy replacement for mercury and glass thermometers. Finally, I want to talk about dry block maintenance. So if you want to keep that dry block working nicely, you want to keep it clean. So you guys are probably the choir here when we talk about maintenance, that it's an important thing to do. If you don't maintain your dry block, pretty soon you won't be able to put the probes in it anymore. The performance may degrade, that sort of thing. So the dry block inserts are made of metal. When metals are used at high temperatures, they oxidize. The oxidation builds up over time. So one of the options that you can use to clean these off is you can use a Scotch-Brite pad, but it's hard to get a Scotch-Brite pad down inside of the well. So we typically use a gun cleaning kit here. So that sort of thing will work nicely to just have a periodic maintenance point where you go through and clean it out, and it'll continue to work well for you for years. The other thing to remind you of is that the dry block's supposed to be dry. If you stick thermal grease in there, good luck getting it cleaned up. It's gonna be a problem for you for a long time. So I would avoid using the thermal grease. The other thing with maintaining your dry block is you don't just buy it once and you just use it until you run it into the ground. You have to recalibrate it regularly. So the recommended interval from the manufacturer for the given specs is 1 year. You may have something that's tighter. Maybe you are more intolerant to risk. You might do it more frequently than that. You might have some sort of a periodic check you do with an external reference thermometer to make sure that over time it's performing the way you expect it to perform. And that would be related to the verifying stability. So that's a little bit on dry block maintenance. Now I said I would talk about an example. So let's take, for example, the 9190. It's got and we're going to try to do a 3-point calibration from -95 to 140. In this case, I could actually set up an automated calibration with the 9190A. I could connect the probe directly to the front of the instrument, and a reference thermometer if I chose to as well, and run an automated calibration that did 3 points from -95 to 140. It would go to those temperatures, stabilize according to the criteria I set, and record all of the data, and then I can get that data out later through either a USB or through a RS-232, and that would be a very easy calibration. I can also do it manually. You insert the probes and set the temperatures to each point. It'll take with a 9190 about maybe 15 minutes to get to the temperature point that you want. You want to allow it to soak for about 15 minutes. You take the data point and move on to the next one. So you could get done in about an hour and a half with a calibration like that. With the 9143, I can actually get to the temperatures in 5 minutes, which is pretty darn fast. But you do want to generally allow about 15 minutes for the instruments to stabilize. One of the neat things about the metrology wells, like this one, the 9190, is there's a stability indicator that'll tell you that, yeah, it's ready to go. Otherwise, you could use, that's something handy you could do with like a 1523 or 1524. You could graph the output and see if it's stable. That's a useful way to tell if something's stable. Otherwise, you wait for about 15 minutes and then you take the point. Now, if I needed to generate calibration coefficients, just the dry block alone is not quite enough to do that. So we'll talk about how to get to calibration coefficients in just a moment. when we're talking about just a simple tolerance test, the verification of the probe, it would go. You would need to know what the appropriate curve is for this probe. So like a DIN curve, IEC 751, ASTM 1137. These are actually three different versions of the same thing, but they might have a Class A, a Class B. Japanese have got their own standard, but this graph shows a bunch of them. And you would just compare, as we mentioned before, the output of the probe to the standard and determine if it was in tolerance or out. And then you could report on that, and if it's out of tolerance, you could toss the probe and replace it with a new one. But if I'm wanting to do something a little more sophisticated, I can generate calibration coefficients specifically for the unit under test. That could be, for example, calendar Van Dusen coefficients. There's a number of temperature transmitters that now take calendar Van Dusen coefficients. PLCs can do that as well. For more of a lab-grade instrument, you also might have ITS 90. And we have this tool called Tableware, the 9933 software, that is able to, you just plug in your reference temperatures, what's your reference read, and then the resistances for the unit under test, and you can calculate whatever type of coefficients you need. And those are available through Transcat. Might also mention as well, while I'm at this point, that Transcat is able to provide calibration services for you if you don't happen to have the equipment you need to do the calibrations yourselves. They also provide equipment rentals if you don't have so much of a workload that you need to own your own instrument. But if you're up to a level where you're going to be doing the calibrations frequently, you have enough workload, it's worth the investment to purchase your own equipment to be able to do those calibrations. Just one final scenario would be automating with your calibration with the 1586A. The 1586A is this data acquisition system to the left of the dry block calibrator. You can hook up as many probes as you need to it, well, up to 20, and you can automate the calibration with any Fluke dry block calibrator using that instrument. It will control the dry blocks, collect the data, and then you can export it to a table, do whatever you need to with it. So we've got a little application note we'll send you about that as well. So this is what the app note looks like. We've got some videos as well that can help you understand what it looks like step by step, how to do the process using a 1586A. So in conclusion here, great option for doing calibration work in a lot of different situations, especially where the environment needs to be clean or you need it to be portable. Get to places that are hard to reach to perform your calibration. It's great. If you need to get to a specific level of accuracy that's maybe better than just 1/10 of a degree, then you want to use an external reference probe. And in some cases, at certain temperatures, you're going to need an external reference just to get to 1/10 of a degree. But for most applications, the dry block itself is going to be accurate enough. So that would conclude this part of the seminar. I did want to let you know about a special offer available through Transcat right now, and that is that if you purchase any of the Fluke calibration dry block calibrators or microbaths or thermometer readouts or even the pressure equipment as well, and you can even combine it with other Fluke purchases such as thermal imagers, whatever. But we have a promotion going that when you make these purchases through someone like Transcat, you are able to get some free stuff, some great gifts with purchase up to a $1,300 value. If you want more information about that, go check it out at transcat.com/deals. You'll also find, I think, a link to the promotion from most of the Fluke and Fluke calibration product pages.
Thanks, Ron. Really nice job. if anybody has any questions or comments, you can email Nicole, who's our Director of Product Marketing here at Transcat, nvanwert@transcat.com. We also have a lot of the information Ron discussed in terms of promotions and free gifts at transcat.com/fluke or on our deals page, transcat.com/deals. Just a reminder, if you'd like to ask a question in response to this webinar, please send it through the question box in your webinar controls. We already have a few coming in, so we're going to kind of move into Q&A right now. All right, so the first question, how often do I need to calibrate RTDs?
Okay, that's a great question. Calibrating an RTD, it's going to depend on the manufacturer specification, and sometimes they'll have one specification for a higher accuracy up to 6 months, and then the accuracy is pretty good over a 12-month period. So you want to follow the manufacturer recommendations, but maybe you have a special requirement where you're trying to have more accuracy than is specified for just an arbitrary 1-year period, for example. It's possible to calibrate them every 90 days in some cases in order to make sure that they're staying in, or another option is to continuously check them at an ice point or in a triple point of water cell to determine whether it looks like it's still in tolerance or not before going through the extra expense of doing a calibration. But typically it's about once every 12 months.
Great. Usually you get a couple questions at this point about getting the slides. Yes, we absolutely send out a copy of the slides, a YouTube link to the live presentation, and along with any information about products or app notes that we've referenced during the presentation. So those will be coming out within the next week, ideally by the end of the week, but definitely in the next week or so. Okay, we have a bunch more coming in through here. Okay, for Class A or Class B RTDs, is the error tolerance linear across the range such that it can be expressed as a percentage of reading?
It's just a little bit more complicated than a percentage of reading. There is an offset, but it is a linear relationship, yes.
Okay, excellent. How about using metal pellets to take up any clearance between the probe and dry block walls?
Metal pellets sounds like something that would probably not be recommended. There have been folks that have used stuff like graphite. Again, difficult to clean out and will build up at the bottom, but yeah, graphite has been used, but I am not aware of anyone using metal pellets. Still, would be best to get an insert that will fit the probes exactly. So a better solution, like say you don't have something that fits quite right, would be that you can get through Transcat a custom drilled insert that will match the probes that you're calibrating if the right insert isn't available just out of hand.
Right, and I was going to mention that we do have a wide range of your inserts available to be bought individually, not necessarily with a unit. Okay, how many decimal points does your dry block reach?
Oh, so yeah, you can get to three digits right of the decimal point for the higher end ones, and I think for some of the field dry wells it may just be to 1/100th of a degree, but usually it's to 1,000th.
Okay, great. Here's another one. How do you know the dry block calibrator temperature is stable enough to take a reading?
Okay, so if you have one of the field metrology wells, the stability indicator will tell you when it's met your criteria. So let's say you wanted it to be within 1/100th of a degree, then you could set that as your criteria, and it will light up when it's met that criteria over a specified amount of time, such as 5 minutes. Another way to determine whether the dry block is stable enough for a measurement is to graph it. So like with a 1523 or 1524 reference thermometer readout, you can actually be real-time graphing the temperature inside of the dry block with your reference probe. And when you can see that it's not drifting upward, but it's stable, that would be a good time to take the measurement. And so if you don't have one of those options, then what the other rule of thumb is, well, let it soak for about 15 minutes and then take the value.
Okay. I have another one here. It's in Spanish. This is going to test me, but I think they're asking about the recommended calibration frequency for the dry blocks. I think you mentioned it. Was it a year?
It's a year for the manufacturer recommends a year for the dry blocks.
Okay, here's one. You mentioned microbaths as a way to calibrate oddly shaped probes. What model would you recommend?
So that depends on the temperature range. Let me see if I can demonstrate, because I think I can pull this up. My internet connection is just a little bit slow because we're running the webinar, I think. So there, with the microbaths, you have some options. Like if I just need to go above zero, the 6102 goes from 35 to 200 degrees Celsius. If I need to go to a really low temperature, like minus 30, 7103 would be the right choice. When you have cooling, that tends to make the that's something that makes it a little more expensive, but it's not too much more. 6102 is probably one of our most common. 7102 is also very common because it covers that often critical 0 degrees Celsius point.
Okay. And on Transcat's website, we have a selection guide for microbaths as well as dry blocks, so that you can kind of compare side by side these units and the specs and limits of each. What else do we have here? What are the typical depths for the wells in the dry well?
They range between around 4 to 6 inches, maybe 7 actually for the metrology wells.
Okay. How can I measure uncertainty if my reference thermometer, which is a Fluke 52, reads only to the 0.1, but the dry block, which is the 9171, reads to the 0.001?
And what was the first part of the question again? How can I measure
uncertainty?
Oh. So this I'm not sure that this I quite get this question. So we've got a Fluke 52, we've got a dry block. There's differences in the resolution between the two. Is that what he was talking about?
Yeah, the 52 reads only to the 0.1, but the dry block reads to the 0.001. So how can you measure uncertainty?
Okay, well, so what happens here is I'm assuming that we're calibrating the 52 with the dry block calibrator, and so there is an additional component of uncertainty created by the low resolution of the Fluke 52. So the 52 is not usually used in calibration, but you could be a good tool to calibrate, and so you probably got connected to a Type K thermometer. What you would do then is to all the other uncertainties that were listed, you would also add an uncertainty for the resolution, and the 0.1 would need to. There's a little technique for converting that resolution number into a standard uncertainty. If you divided it by, it's a half digit, and you divide by. Well, I'm not gonna. Well, I'd have to. I could get back to you with the correct answer for how to determine the uncertainty there. But it's basically you've got an extra half of a degree. No, not a half a degree, but 0.05 of a degree uncertainty to add in there because of your lower resolution.
Okay. Yeah, we'll send you that question, Ron, and we can go through it if we need more explanation offline. A couple more here. I know we're running up against time. Can all the Fluke dry block calibrators be controlled via a Fluke 754 or 753?
Yes, yes they can. That's a great thing to do. It's a wonderful feature.
Right. Okay. What type of input connector for the external reference sensor on the drywall? I have a 5627A with a 1502A. Would it just be better to monitor with my 5627A, 1502A setup?
Yeah. So if you have a 1502A that's connected to a 5627A, that works just fine as an external reference thermometer. It's a great combination. The 914X series has got, if you choose the process version, has got inputs that are specifically designed for a smart connector. So it's going to look a lot like the 1502A DIN connector, but it's got an extra terminal in it for a computer chip that keeps all of the calibration information for the probe on it. So all you have to do is plug the probe into the 9142 or 3 or 9144, and the display will immediately read the calibrated value for that reference thermometer. It's kind of nice. You don't have to insert any calibration coefficients yourself.
Okay. Do you have any suggestion for checking plastic-coated wire thermocouples with only a small metal part of the thermocouple that's exposed?
Okay, so when you've got the tip of the thermocouple exposed, you want to make sure that it's not touching the metal on the dry block. So when you have it inserted, you got to lift it just a little bit from the bottom of that insert, because it's conductive material and there's a heater going, and so you're going to get some electromagnetic interference if it touches the bottom. So that would be one issue. And they mentioned some sort of coating.
Plastic coating, yeah, up until the tip.
Okay, so now the plastic coating, of course, you just got to be careful that you're obviously not going to take it up to 200 Celsius or something like that. You got to keep it under the range, because that sounds like a mess I don't want to clean up if the plastic melts onto the insert.
Okay, and the last two here, they're both application related. Is there a technique for accurately testing temperature switches, and then can you use dry wells for calibrating surface mount RTDs?
Oh, okay. So for temperature switches, actually most of the Fluke dry blocks have got a connection for being able to do a temperature switch calibration, where you wouldn't have to have a separate DMM. You just connect your switch up to the terminals, and when you take it above the switch point and down below, it'll trigger the dry block to record the reading so that you can calculate the deadband afterwards. In the case of the field metrology wells and the metrology wells, there's actually an automated program for that. So you connect the switch and run the automated program, and it will actually calculate the deadband for you. So yes, you can. Now the question about doing the surface sensor calibration on the dry block. Well, as we've talked about earlier, there's this thing called axial uniformity, and so there's a difference between the temperature at the bottom and the temperature at the top, and the calibrated sensor is all the way down at the bottom. And so while some folks might suggest that you can do the calibration by surface calibration with a dry block, I don't think I would recommend it. There's some large uncertainties there. We do have a surface calibrator specifically designed for doing that.
Okay, excellent. And then I had one question come in about would I need to ship my dry block out to Transcat for the recommended yearly calibration? Yes, that's one option, and we do have 18 plus labs across the country you can ship to. There's likely one in your area. We also perform on-site calibration services, so if you have a unit or several units that you want to get on that calibration schedule, we can come to your location as well. And the person who asked that question, I can follow up with you offline. But yes, you could certainly send to Transcat, or we can come to you. So that's going to conclude our Q&A for today. I appreciate all the questions, and Ron, thanks for all the answers. There were a lot of them. If you have any further questions, or you'd like to find out more about our Transcat's products and service offerings, contact us at 800-800-5001. You can email Nicole at nvanwert@transcat.com, or you can visit us on the web. Thank you for joining us today, and we hope you got something out of the presentation, and you continue to join us on future webinars. Thank you.
Thanks, everybody.